So last time I tried to present from this laptop. All kind of funny things happened, but we'll see. I hope that it's going to go better. All right. So I have 3 topics that I'd like to talk about. And obviously, I can't give just to any of these topics. But I just wanted to, like I was reflecting on the title of the workshop, New Directions in Reinforcement Learning. So it's new for a guy who's been here for, I don't know, too many years. And so I'm going to present things that are kind of newish to me and like maybe underexplored in the field. And at any time, if you have any questions, please raise your hand. I will try to attend to you, and we can clarify issues if there are some issues to be clarified. All right. So let's get started. So I'm going to talk about curiosity, unobserved rewards, and functional approximation in reinforcement learning. I mean, like when you do neural networks, either you like deeply study neural networks or you're a user of neural networks. If you're a user of neural networks, then you kind of like stay at the high level usually, and then you can just think about them as some powerful tool to do functional approximation for you, and then you can ask the question, how do you do that? So that's the third part. All right, curiosity. Well, that's the thing that killed the cat, but I actually took a photo, but I didn't have time to upload it. So no one needs to be convinced that curiosity is important, how important it is for any intelligent agent, but what it is. Like, how do you formalize curiosity? How do you study curiosity in a theoretical framework? So here, in the first part, I chose to talk about an old paper by Peter Auer and Lim, Ching-Kun Lim. And at the beginning, Peter Dayan was also on the team, where they tried to formalize some notion of curiosity. And they have some really curious results about it. And then recently we revisited it and we spiced it up because the word is nonstationarity, and we asked the question, okay, how do you keep your curiosity up when the word is changing underneath you? Right, so that's the first part. So how do we model curiosity? So obviously we want to have a control process. You have to interact with the word, and you're running experiments. That's curiosity, right? And you want to gain knowledge. And we like to keep things stochastic because it makes things more interesting, and maybe it's even more realistic. It's definitely way more interesting if the word is stochastic. Now here come some really strong simplifying assumptions. So I'm going to assume that the state space, so there's a controlled Markov process. So far, so good. You have actions. You have state transitions. The state space is going to be countably infinite. All right, so you might say that, wow, that's really limiting. But OK, you have to start somewhere. And at least it can be infinite, right? So that's where you're starting. And the other big simplifying assumption that connects to the second part of the talk, you observe the state, right? So you make a step. You choose an action, you make a transition with your state, and you observe the next state. Control people would immediately frown upon this, but in AI, you kind of like have very good sensors, and then you can just like hand wave it away for a while, at least. So that's what we're going to do. And here comes the even bigger simplifying assumption. This is just to say that you have a mom that takes care of you, right? So you can reset to an initial state. Right? So if you're learning about an environment, and it could have traps, and then you can die, and it's really bad. Or maybe you just get lost in the woods, right? So ideally, you want to just cry for your mom, and then your mom takes you home, like puts you in a bed, and then you can continue learning next day. So that's reset. So I'm going to assume that we're going to have reset. It's actually necessary to get things going. All right. And so what's the goal? So you can formalize then the goal of a curious agent living in this controlled Markov process as the goal of discovering the set of reachable states. And if it's doing its job well, then it should be doing this discovery process as quickly as possible. All right. So what's the performance metric? this is a bit complicated. So at the high level, you want to maximize the number of reliably reachable states per time step. But to talk about this, we have to go through some like kind of like fine reasoning. I'm not going to be able to convey to you like why do you have to define things in specifically this way, but there are counterexamples that show that like simpler definitions just don't work. Okay? So how do we do this? So you fix an arbitrary partial ordering on the states. This is not known to the learner maybe. And you fix L. L is the horizon. So you want to discover the set of states which are reachable in L steps on average, an expectation. And then you're incrementally defining with respect to the partial order this set of states that are reachable in L steps with respect to this partial order. The reset state is in this set. And then if you can find a policy that reaches another state in L steps on the average such that the policy stays within the already defined set of states, where you use the partial order to restrict the set of states, which is in the set, then that state is also in the set. Okay? So this partial ordering is just like some enumeration. So it gives you an ordering over the states. And then the set of reachable states is not sensitive to this partial ordering. So you take all possible partial orderings, and you say that the set of reachable states in L steps is the union over all possible partial orderings. And you can show that simpler definitions, as I said, didn't work. And you can also show that this is actually such that there always exists a partial ordering such that this reachable set of states is reachable set of states with respect to that partial ordering. Okay, so in a way, the learner needs to figure out this order in which it should visit the states and stay safe. And luckily, because we are in an infinite space, well, you can also prove that this is finite, so you have a chance to discover in finite time all reachable states which are defined this way. All right, so very quickly, the algorithm is just a variation of the upper confidence bound algorithm, and the way it works is like a breadth first search kind of thing, but it's like spiced up or beefed up. So the algorithm has a set of known states, and then it also knows about the fringe states. So these are the fringe states. Let's see whether this, oops, no, that didn't work. Okay. All right, so these are the fringe states. Okay, so the algorithm also has a fringe states, and then when it discovers that it can get reliably from, okay, so there's S0 reliably to a new state, then it will go there and it tries each of the actions L number of times, roughly, to discover new states. So these are the new states that are discovered. So when it tries these actions, very often it will go back, right? So it doesn't add any new actions. Then it has new fringe states. And it considers all these fringe states and then just like thinks optimistically about them. It thinks that like, given all the uncertainty about the world and given all my knowledge, which of these states seems to be closest to the initial state? So that's the optimistic part. You take into account the uncertainty there, and you select that. And so that was a proposal phase of the algorithm. And once you select that, you try to verify whether your proposal was correct. So you follow the policy that you proposed to get to that state, given your knowledge, and you see whether you can get there. Okay, so you have some time modes here and there, and you try it for a number of trials, and if sufficiently many trials are successful, and get to this state sufficiently often, and within a reasonable amount of time, then this becomes a known state, and the process continues. And you stop when you discover that there are no more known states. All right, so what's known about this algorithm? So the algorithm basically, well, it has to overshoot a little bit the set of states that are feasible because it can't really distinguish, no algorithm can distinguish between 1 plus epsilon times L reachable states and L reachable states. It has to overshoot a little bit. It overshoots a little bit. And for each of those states, it's going to spend some certain amount of time, but the time it spends on discovering the states is going to be proportional to the size, linearly up to log factors, proportional to the size of the set to be discovered. And then for each of the states, it's going to spend some time. It's cubic, unfortunately, in L over epsilon. Okay, so there's this epsilon approximation factor as well. And so that's okay. So you can, if you're worried about that L is the input in the algorithm, then you can introduce sort of a doubling trick and some union bonds, and then the algorithm can just go on, and this is the true continual learning. It just goes on and tries to expand the set of reachable states and does this in a reasonable way. I really like this work. One obvious question is whether these bounds are optimal in any sense, right? Like, can you improve this cubic dependence? It seems a bit harsh, this cubic dependence. So that's a question. And now about non-stationary words, right? So winds change, the word changes, the agent's viewpoint is limited, and because of that, even if the agent is living in a stationary word, maybe the word is going to appear non-stationary, so there is much value of thinking about non-stationary words. In particular, you talk to any practitioner who is running algorithms, reinforcement learning algorithms or control algorithms, they will tend to frown upon if your learning rate goes to 0. They'll be like, no, like learning rate can't go to 0, like the word is going to change underneath you, right? So you have to be prepared to changes. There will be always parts which you don't see which change. And so what happens to curiosity if the word changes upon you? So simple question, how do we model this? So if the question we ask is that, all right, so the agent has this lifetime, it just lives its life, and the word changes f times abruptly underneath the agent. So the transition probability kernel changes f times, not known to the agent when the change happens and how the transition probability kernel changes. Maybe it changes in an irrelevant way, maybe it changes in an absolute relevant way from the point of view of the agent's skillfulness of getting to the reachable set of states. And now the agent has to go on, and it's kind of question of like how much time the agent is gonna need. Like how should the agent discover the changes, first of all, and how much time the agent is going to stay in this miserable state of not knowing that the change happened underneath them. So they think that they are skillful, but they are not, right? So that's the metric that we want to minimize. So you might think that, okay, if it takes, I don't know, W of work to find all reachable states, then maybe if you have F changes, then the number of states, the number of time steps when the agent doesn't know what to do, it's not skillful, it should be linear proportional to the number of changes. And so you want to ideally shoot to that. Spoiler alert, we're not going to get there, but getting somewhere. All right, so this is just to say that either the algorithm is competent, incompetent. You want to minimize the number of incompetent steps. Okay, so how can we do this? Well, there are some difficulties that we are going to face. We want to recycle the previous algorithm. So you take the previous algorithm, and it starts to build a set of reachable states. As it does it, things may change underneath it. But let's say, keep it for simple, that didn't happen. Then things can change afterwards. So once the building phase is over, then the agent still has to go and then check time to time whether there are any new states which are reachable, or any states which are reachable are not reachable anymore. So it has to keep going and then keep experimenting. So that's the checking phase. And so the agent is going to do that. And for the checking phase, to check whether any new states appear, it basically has to kind of like repeat the building process, right? Like it has to try to discover new states which are reachable. And so if that takes too much time, then okay, it knows that the environment changed, and then a new phase or a new round begins. And so So what's the issue with the building? So the algorithm just cannot know why building, whether what it's building is correct or not. Because it's busy with doing something and then something else changes somewhere else in the environment. So how can it know? So the solution to this, which we came up with, is quite kind of like simplistic. It's like what probably everyone would think about. You start many parallel processes that are staggered, like you start some later building processes, and you hope that one of them is going to finish. And then once that finishes, then you go into the checking phase. Okay? And so that's what you do. That's all. And then you have to play around with like the scheduler, that because you only have one lifetime, so you only build. Like, so you have to simulate that you're doing these things in parallel. So that's the algorithm. And the result that you can get roughly is the follows. So if you have F changes in the environment, and then the work usually is W. So unfortunately, we can't get the F times W bond, but we get an F times W squared bond, which comes from this staggered simulation process. So again, there are these open questions. Is the quadratic dependence necessary? Is the cost for building in a stationary environment the best possible that we have seen? And of course, you can wonder about how to extend all this to non-tabular environments. All right, I'm done with the first part. It's a little bit slow. Any questions? I'm going to be around for the whole workshop, so like in the break, if you have any comments, questions, please come to me. All right, so second part, it's, I already mentioned that it's kind of weird that we assume that the states are observable. So any control people would like immediately reacted, like, that's outrageous, you can't do that. But okay, we still do this. But we also assume in reinforcement learning that the rewards are observable, which is maybe even more outrageous if you think about it. Like there are many, many processes where you can make inferences about the reward, but you can't directly observe the reward. So you know that like the reward is bigger than 5 or less than 4, but you don't know exactly the value of the reward. It's not about noise. It's just like you have like limited information about the situation. So there's latent variables going on. So what happens when the rewards are not observable? Obviously, this has consequences for planning. Planning can become really hard if you're in the PALM-DP setting. And it has consequences for learning. Even for learning, you may need to take actions that just collect you information about what the situation is, right? So if you have some latent information there in the environment, then you want to investigate, like open that fridge and then see what's inside before you take further actions, right? Okay, so I like to simplify everything to bare bone. That's why I work a lot in bandits as well. And DPs are very, very complicated. If you want to study exploration, maybe you start with bandits. That's cool. And so we can do the same. If you take a PALM-DP where the reward is not observable, and you just assume that the state is an IID process, you get what is called a partial monitoring problem. Okay. So how does this work? And so this is the topic of this part. So here's an example to illustrate it, to make it a little bit more concrete. So maybe this is plain in rounds. It doesn't matter, or you have this graphical model. So the agent can choose to show a web page. And there's a user coming to a website. And the user has its own interest in everything, complex personality, which we know very little about, right? And let's say you are really nice and you want to maximize the agent's happiness. Like, how can you maximize the agent's happiness or user's happiness if you know so little about the agent or the user? So maybe sometimes you can take some actions that tell you something about the internal state of the user, and by that you can figure out what would make the user happy, right? So you have to take explicit actions to figure out what the user likes, but poorly for us, we don't necessarily observe directly what the user is happy. We only observe what the user does. For example, it clicks on things. All right. So you can formalize this. There is an environment. The environment choices are X. there's an agent, action choice, the agent's choices are actions, they're A, and they're observations, and they're unobserved losses. And you can do this in a sequential fashion, so the learner or the agent is given these two maps, the loss map and observation map, and there are all these rounds, and the environment is going to choose the outcomes for the given round, and the learner chooses some action, and the learner suffers a loss. This remains hidden, and the learner observes the observation. You might ask the question, okay, in this situation, what should the learner do? Well, first, the question is, what is the learner trying to achieve? Let's say the learner is trying to minimize regret, which is nice, because then you don't have to make assumptions about the environment like that. The outcomes are ID or something like that, but you can just study the worst case and many more things. So this is kind of neat because there are many examples which kind of fit in this framework, but I'm just going to skip over that and just go to the main thing. So for games of this time, the main result is what is known as classification result, which was the outcome of many, many years of research. And many people contributed to this. And this classification result says that if you take a finite partial monitoring game, finite game means that finitely many outcomes, finitely many actions, no other resections. Then there are 4 possibilities in terms of the scaling of the minimax regret for that game. And the 4 possibilities are shown here. And you can describe in a very nice geometric fashion. Somehow this game structure gives you some nice geometry on the simplex. And based on that, you can describe which category a game falls into. Okay, so a lot of time being spent on like these 2 cases. These are obviously trivially hard games. They're not too interesting. These are trivial games, trivial easy games, not too interesting. It turns out that these are the games which are bandit-like because the regret scales with square root n. And these are the hardest to design good algorithms for. So there's been quite a bit of work on that. And so what do we have up to now? Well, the first thing to notice is that classical algorithms that are aimed for bandits just don't work. Like if you try to apply a bandit algorithm, it doesn't care about the information, right? It just cares about the losses. So neither optimism or tensor sampling or exponential weights are going to work. There are many more, some more complicated algorithms, which are, I don't know, like solving fixed points for Markov chains and then doing fancy things which help you to prove the theorem, but they're really, like if you try to implement them, really horrible algorithms. Okay? So what I'm here to tell you about is a new result that's an archive. It's together with Stoll Lattimore. There's a new algorithm which is simple, works well, works in all possible cases, and it's competitive with existing algorithms which are specialized to specific cases like bandits. In terms of practical performance, it gets the best bonds in all cases that we have checked so far. So, and the algorithm is really intuitive. We are still going to rely on exponential weights. So everyone kind of knows exponential weights. You estimate the losses, and once you have the loss estimates, you're exponentiating them, and then that creates a probability distribution after normalization. And usually here we just like rush and try to play from that distribution. Here we're going to do something else. We're going to say that, okay, let's like just not rush this so much. Let's come up with another distribution because we also need to care about information. So in this other distribution, we're going to depart maybe from exponential weights distribution, and because of that, we're going to suffer a loss. So that's the loss that we're going to suffer. So we're thinking about choosing this distribution P, so we're going to pay. We're ready to pay if we gain information. So how do you quantify information? Well, people have all kinds of ideas. We thought that the best is just to look at the regret bonds that you can derive. And from the regret bonds, you can see that there's a penalty for playing whatever information that comes from the analysis of the resulting algorithm. And so you include that in the optimization problem. So whoever is familiar with the analysis of exponential weights, is familiar with this term. This is the term that you always have trouble keeping bounded. So here we just say, yeah, like, I don't know, like, let's just solve this optimization problem where we optimize for this distribution. And we also have to optimize because there's so many different ways you can estimate the rewards. So that's like a linear constraint on this function g. So that's like a linearly constrained problem. And you're trying to minimize this. And this is a saddle point problem if you wish. But it's a convex problem. So you solve this. And then you simply play from this distribution PT. OK? And after that, you update your loss estimates based on your estimator that came up from the optimization problem. So the idea is to jointly optimize the estimator and the distribution, care about the regret bound. And this does the trick. So this is a single algorithm, works in all of these cases, gets the best regret bounds. I won't bore you with details of like experiments, but like we're very happy that the algorithm is actually practically a good algorithm. Like it beats AXP3. Okay, that's maybe not a big thing, but like it's a general algorithm, so it's not bad. And it seems to be doing the right thing. So in these experiments, just for battery bandits, it's okay, too many details. Like you can ask me, yes?
In the case of non-stochastic bandits with full monitoring,
yes.
Become something known like XP3 or some other known algorithm? Is it a special case?
Oh, the question was whether this algorithm becomes a known algorithm like AXP3. No, it plays differently than AXP3. Brandon McMahon had a similar idea in a different setting, actually. So, but it's different. Yeah. Okay. The proofs, though, work the same way. Like, you basically say that the optimization problem includes the choice that AXP3 would choose. Therefore, we have a regret bound. We don't have to work really hard. Yeah? Okay, so more experiments. We're always blue. Smaller is better. It's always very good. Anyways, conclusions. So partial monitoring is way more ambitious than just bandits or whatnot, like different versions of bandits. And so I learned from this that maybe it's not that bad to be ambitious sometimes. It's a double-edged sword. It took a long, long time to come up with this algorithm, but it's a very good algorithm, I think. Well, we need more experiments. The optimization problem is a beast. So we are working really hard to make this optimization problem nice. It tends to break all the solvers. The nature of it is that, like very close to the optimum, there are some directions where the surface is very flat. Other directions, it's really, really curved and like really high derivatives very close. So if you don't have a superb adaptive solver, then it can break it easily. But we managed to find some solvers that can solve it. What happens when the outcome space is large or infinite? Can you generalize it to other settings? I think that there is some space for exploration here. All right. Okay. Last part. I don't know. Any questions for this part before we move on? Yes?
Sorry, this is a very basic question. But
Yeah.
in the last setting, the partial observability is that you don't see the reward.
Yeah.
So then how is the loss function? How is the regret defined?
It's defined with respect to the... Yep. Yes. The question was that in the last setting, you don't observe the loss or the reward, and how is the regret defined? The regret is still defined with respect to the loss. The learner is given the loss function for all possible outcomes. What it doesn't see is the outcome chosen by the environment, so it can make inferences about what the loss would have been based on observations that it has. So that's why it's, but the regret definition is just the same. There are, okay, we can take it offline. Like there are more things to say about this, but like, I think that in the interest of time, I just move on. Okay, good. All right. So the last part is about this quest for algorithms in reinforcement learning which are function approximation friendly. And I've been working on this topic for quite some time by now. And why do you need this? Well, obviously the world is huge and it's very complicated and you need to do approximations. And the bad news is that our algorithms tend to be really sensitive to how you're doing approximations. So you can do approximations in many different ways. I'm going to present 3 different ways. And then we can discuss like advantages and disadvantages of those. So in general, what are we interested in? So in general, you come up with a model which simplifies some aspect of the environment, and that's going to result in some errors in your policy, and your policy is going to be less than optimal, and so you want to bound this suboptimality gap of your policy as a function of like how good is the model that you're working with. There's been a lot of work on this. All right, so 3 different results. So first, I'm going to talk about a framework, adaptive linear programming, or approximate linear programming. We should make it adaptive. And some results there. Then factored linear models, and then model-free around. All right. So approximate linear programming. You probably know that MDP problems, discounted setting, undiscounted setting, many settings, can be rewritten as a linear program. And very early on, people were like, hey, this linear program has too many variables, it's the number of states, it has too many constraints, number of state actions. So why don't we introduce some approximations? For example, so the number of variables is the number of states, and that encodes the value function. So why don't we just think that like, those can be encoded with k parameters instead of parameters proportional to the number of states. So they live in a linear subspace. So you can do this subspace reduction. So that results in this, that you have this phi, which is a matrix, R is a vector, it's a low-dimensional quantity, so this expands this into a high-dimensional quantity. And then you minimize this. C is just a vector that's normalized so that it sums to 1. Any vector is going to choose. Alpha is the discount factor. G of A is the reward vector underlying. It's a high-dimensional quantity for each state. So the dimensionality is the state. For each action, it's the reward vector. This is the next state distribution. It's a Markov transition kernel. And so this form should be familiar, except that here you usually have all these constraints for all the actions, so without this summing. So I just add this summing because like we love linear, right? So we're going to project the constraints as well. So if you go to the dual space, that's kind of like saying that, oh, maybe you're doing some approximations to the in the dual variables, which are occupancy measures in this case. But anyway, so the W are non-negative valued. And maybe you can normalize them because you're not losing anything. And then the question that you ask, okay, so this way, what's the gain? You're reducing the number of constraints, right? It's a projection. And now you have much fewer constraints. So previously people were sampling, whatnot. This is kind of like, you know, like the smoothened version of sampling. And so you can ask this question, okay, if I solve this problem, how good is the solution? What can I say about the quality of the solution to this problem in relation to the quality of the optimal value function? And you can get this, this result. Let's say it's the following. So if you read out the solution to this problem, so this is the solution to this optimization problem, and you expand it to the big space, you have an approximate value function, and you care about how much this deviates from the true value function. You're in the generative model, so knowing just this difference and plus doing some simulation may allow you to act near optimally if this bound is small, if the bounded quantity is small. Okay? So some further computations would allow you to act well. Okay, so we want to keep this quantity small, and in this theorem, what you see, and this is joint work with Chandru and Shalab, you can see that this quantity scales with epsilon. This is the best approximation to the optimal value function with the subspace that you have chosen, and then there is some blow up happening, and you can argue, I think, that that blow up is not possible to avoid, and there is some additional term. And so classic results for ALP would have the first term and not the second term. Classic results don't compress the constraints, so the price of compressing the constraints is the second term. If you over compress the constraint, you might arrive at a problem where the feasible region is empty and you get nothing. So that's the problem. Of course, you have to be careful, and then there are thoughts about like how to avoid that. The first thought is that, well, just look at these quantities. So what are these quantities? So these quantities, these are two value functions that live in a high-dimensional space. They are the least upper approximation. The first one is the least upper approximation using your basis of the optimal value function. The second one is similar, but given the constraints. That also takes into account the constraints. And so the difference between these two is the additional price for doing this compression. And all right, so you might think, okay, this is maybe acceptable. It's kind of weird that you have to consider this upper approximation. So can we do something different? All right. So yes, maybe you can. So in fact, if you go back to the literature, to the work of Witt, he was the first guy, I think, who considered just a question of like, hey, I want to act in one MDP, and I have this other MDP. I'm solving for the optimal policy in that MDP, and how well am I going to do in this original MDP, right? So what's the policy error? And so he came up basically with this result that tells you that the error is bounded between the difference of these transition kernels, so they also hide the actions, so they're like higher dimensional, and the value function for the approximate model. Like, so the difference doesn't have to be small everywhere, but inconveniently or not, it has to be small at the value function that you're going to compute. Now, if you don't know anything about that, maybe you know that it's going to be bounded, that you can get a result that just says that if these are closed in L1, and so you can get an L infinity bond, then Herder's inequality tells you that, okay, L1 closeness of transition kernels is sufficient to get good policy error. Question is, can you do better than this? I'm like, yeah, this is great, but maybe by assuming additional structure, you can do better. So one models that I really like, and it seems that this is also picking up in current literature in a different context. So here I'm just thinking about like it's model-based.L. So someone gives you this approximate model, you solve it, you read out the policy, how are you going to do? And so one of these models, like one of the class of models that I really like is these factored linear models. So in these factored linear models, there's a lot of stuff that I won't be able to explain, but the gist of it is that the transition kernel has a factored form, such that you have one kernel which goes to low dimensional space. So this is like an analysis kernel that goes to low dimensional space, and then there is another kernel which expands back to the high dimensional space, and then you suspect that if this factorization is good, then at least based on the previous result, you should get a good result. So what's good about this? If you do this, you can do all the computations sometimes in the low dimensional space, and so you can be, your complexity is going to scale with the dimensionality of the space that you're projecting to, like, let's say, RD here. And there's a lot of special cases, which a lot of previous models that people considered, which are special cases of this. It's kind of neat. All right, so what is the result that we can get in this case? It's a bit complicated. So this is about the error of the policy, so how much the policy loses compared to what it would get if it was the optimal policy, and it's bounded with two terms. And in two terms, what I would call your attention to that is that there is this mean. So you can choose the smallest of these two quantities. The second quantity is just the result from width. Okay, so that's the same thing. U star is essentially the fixed point, the optimal value function for the compressed model, okay, for the approximate model. So that's its result. You can take the mean with this other quantity as well. But in the other quantity, you can plug in the optimal value functions. Your model has to be accurate only at the optimal value function, and also the value function of the policy that you read out. So this has two quantities. So what's really notable about this, that the 1 over 1 minus gamma factor doesn't apply to this. So this is a high dimensional quantity whose norm you want to keep small. And it's not divided by 1 minus gamma. That's really neat. We don't like the 1 minus gamma divisions because it kind of shows a blow up is the horizon of the problem. And that's really inconvenient. And here you have this other term, but in this other term, you're projecting to the low dimensional space before you compute the errors. So that's kind of a neat result. All right. So of course, there are questions like, is this bound tight? This is just talking about this factorization, which is by and large state abstraction. But you would want to do time and action abstraction in a seamless fashion and apply something similar to this, to that case. I don't know how to do that. How to learn this efficiently? Well, this factorization comes up very naturally. For example, if you consider Cantor mean embeddings. And the problem is that if you have n data points, then all your algorithms are going to scale with n cubed. You can try to apply random projections and other techniques. What we tried didn't quite work. So it's a question of how to make this actually work, at least in the non-parametric world. All right, and so the very last part, for which I have 1 minute, 0, okay, is we started late, right? Yeah, okay. So the very last part is a different word. It's online learning, and it's model-free, and it's motivated by talking to colleagues at DeepMind. So like it seems that like model-based we do a little bit, but we're not nearly as successful with model-based algorithms at the moment than model-free. It's a good question, why? But since we are more successful with model-free algorithms and people love them, so why don't we make them even more efficient? So here the question is, how do you design model-free algorithms for RL, for which you can state some theoretical guarantees which are reasonable when you're using function approximation, like neural networks in the background, to approximate value functions. So that's model-free RL, right? Like you just like go and estimate value function and try to change your policy, and you do that in a clever way such that you keep everything under control. So it's the online setting. So if it's an online setting, then you care about the regret. So that's how much you lose compared to acting optimally from the beginning or acting according to some fixed reference policy that you care about. So that's pi star. And there is this quantity called the pseudo-regret, which just compares the average performance gains of the policy that you're executing at time step t. So that's pi of t to the average gain of the optimal policy, and the difference between the pseudo-regret and the actual regret can be bounded if you have mixing MDPs, and otherwise, like, I just don't care. I think pseudo-regret is good enough to control it. It actually tells you how skillful you are. Okay, so you want to control the pseudo-regret, and there is a beautiful formula that tells you an equality for the pseudo-regret. And you just look at this formula, and you just say, Elad, what will you say? This is just online learning, right? Okay, so for every state here, You have this linear expression, right? So you want to keep this regret small. So this is what you choose. It's a distribution. And it takes the inner product with this loss. And, or reward, I forgot. I think it's a reward. No, it's a loss, right? So we are in a loss framework because pi star is the second. And so the Q functions are for cost. And so you have to compare it with the best choice in hindsight or whatever. Like this pi star, it's just fixed, right? Like a fixed reference distribution. For every state, you have to control these quantities, or like, I mean, like you better control them. It's sufficient to control them. If you control them for every state, then you'll be doing fine. And it seems like this is just online linear programming or online linear optimization, right? This expression is linear in this distribution, linear in the distribution. These loss functions, okay, they're complicated. We don't know them, right? But that's the cool thing. Like afterwards, you do something, maybe you learn something about them, and then you can control them, right? So you can do this decomposition because you never see the action value function for your policy. Yeah.
Why do you measure the value of the player according to V pi star?
Oh, this is an identity, so I didn't choose this. It's just like I love it.
But
I mean,
you play some kind of policy, maybe I missed something. I mean, you play policy pi t, then you have some other distribution, right?
yeah. So like, of course, this expression is symmetric, so you could put a pi t here, but then this would be too complicated and it wouldn't be very helpful for what I want to say. It's an identity. It's like you can prove that it's just Ban's equation after a few algebraic steps gives you this. We can talk about it. Yeah, it's pretty cool. It's called the performance difference lemma that gives you this. Yeah, it's not super intuitive, but this is how it is. Okay, so Qt is not accessible, but the learner is going to estimate Qt. Qt is the action value function of the policy. And so you can write this other identity, which is decomposes this difference into these three different terms. These two guys just introduced, they cancel each other. You can control the first quantity by using online linear optimization, OLO. As long as you can keep these guys bounded and like you adapt the step sizes, so there are some nastiness there, but you can keep this under control with online learning tools. And we're going to assume that you have strong function approximators. So the function approximators can control the other two terms, right? So they're just approximation errors, like how close is Qt to Q hat t? I'm like, if you collect more data, it's going to be closer. And then it depends on your function approximator. Okay, so there are some details here that I'm hiding, but just like jumping to the next step, so what is the algorithm that results from this? So the simplest algorithm that you can use in online linear optimization is exponential weights. You plug in exponential weights, and lo and behold, you get this version of policy iteration. So in policy iteration, you just do this, which we call Politex. Policy iteration with expert advice or whatnot, or exponential weights, I forgot. Where you have this entropy regularization, if you wish, or this exponentiation. It's also similar to Poyak averaging, and then you can intuit about that, like maybe what this does is that allows you to run things for shorter phases because there is some variance reduction happening. And anyways, so if you do this, then you can get a meta result like this that says that if you're able to control the function approximation error in every iteration, like usual parametric rate, then you can read out the regret rate for the whole thing, and it's going to be t to the minus 3/4. That's the average regret per time step. It's a bit slow. I don't like it that much, but what's nice is that if the floor of the error is epsilon naught, then that just appears there in the regret, which is unavoidable, but that's the best possible that you can do. There are a few issues, though, with this. So can we actually do this? So a good test for that is to study linear value function approximation. It happens that, well, that already shows you that the errors can blow up. So the error of the function approximator that tries to solve a fixed point equation can be much larger than the smallest possible error that you can get with a linear subspace. So that's open problem number one. Like, can you do something better than that? Maybe no. So you can refine this. So the problem, another problem is that it was hidden that you kind of exploring all the actions indefinitely. If that is not happening, then you better separate state value function from action value function, add some exploration of the actions, and then you can refine the results. And here you only need to assume that all policies are exciting the features. So the underlying data Gramian matrix has an eigenvalue bounded away from 0 uniformly over all policies that you will encounter. So that's still a pretty strong result. So can we refine it? Yes, you can. If you go back to curiosity, like, so there we had a policy that was just going on and exploring the space. So if someone gave you a policy that does that, but okay, it doesn't have to explore the space, it has to explore the feature space, then you can use that policy to excite all the features, interleave the execution of that. Complication is that now you're in the off-policy regime, you have to use off-policy learning. We don't have very good results for off-policy learning and controlling the function approximation error. So you can master things and still get the regret bound, but it's not super nice and it doesn't feel like a finished product. So there are a bunch of obvious questions. Can we do better with other online learning methods? Is averaging really necessary? How do we design better value function learners? All right, so with that, I need to stop because people want to get some, I don't know, is there coffee? Coffee? No coffee. A break. People want to get some break. All right, so we talked about curiosity, exploration by optimization, and RLN generalization. You can see that lots is going on, and it's exciting times. Thank you.